So, welcome to the next lecture on this topic on this course. So, the last class we discussed about the APT instrumentation, and also we little bit detailed way we understand the function of delay line detectors, especially the MCP and delay line detectors, which is related to the position sensitive detectors, both of them, correct. And we have estimated the position of hit of the electron cloud on the delay line detectors by measuring the time to reach the both the ends in both the directions, like as x and y, okay. And the total time of flight for the ion can be measured as uh, the time taken for the electron cloud to reach all the ends like x1 y1 x2 y2 and divided by 4. So, that was the thing which we discussed about the measuring of position and time. Now then we also introduced I think in the last class that the pulsing techniques. So, little bit more detailed way we will talk about on the pulsing techniques. So, now we will describe the pulsing techniques. Pulsing techniques. As I introduced before, the pulsing techniques can be two ways. One is HV, one is thermal pulsing. Okay, and HV pulsing. So, thermal pulsing by using laser. It is mostly related to the photon assisted evaporation, field evaporation. HV pulsing, we are pulsing the voltage, okay, and this will be for fast HV pulses. This is around few nanoseconds used, okay, and the shape of this HV pulsing depends upon the time dependent evaporation probability, okay, and also the modeling of or shape of the HV pulse. So, it has two functions, correct, these two functions. So, the shape of the HV pulse, it depends product of these two exponential functions. So, according to the evaporation rate, the adsorbed atoms are likely to field evaporate at a frequency which are related or which are near to the vibration of surface atoms, okay. So, frequency means, as I told you, mu 0, which is around 10 raised to the power minus 13 to 10 raised to the power minus 11 per second, fine. This is the frequency. So, as the field evaporation is related to the probability, not all the atoms will be evaporated at the same time or same instant, okay. Not all the atoms are field evaporated at the very same instant across the duration of pulse. It means that if you have a HV pulse, some of the atoms may get field evaporated at this location, some of the atoms may get field evaporated here, some of the atoms, depending upon the local vibration frequency of that particular atoms, correct. So, this uncertainty can lead to the resolution, to the mass resolution, to the lower mass resolution for okay, or to it will affect the accurate determination of mass to charge ratio, okay. So, elemental identification will be difficult, it will not be resolved easily. because of this uncertainty. It means that the atoms at if there is a HV pulse here, the atoms can feel evaporate when your HV is in this position. It can feel evaporate here, it can feel evaporate here, it can feel evaporate here. This will induce a spread in the mass to charge ratio peak. Okay. So that is depending on the instant at which the ion is created, it will accelerate at different stages of the varying field. Your field is varying, correct? So it means that for an atom to field evaporate, it is not require full energy of the pulse. Some of the atoms can field evaporate at these locations. Fine. This is called energy deficit. This is called energy deficit, and energy deficit depends upon the velocity of the ion and also mass. Okay. So because of this energy deficit, there is a spread in the mass peaks, which directly affects the mass resolution of the during HV pulsing of the specimen. Okay. So for HV, to induce field evaporation requires the specimen should be electrically conductive. So material with a higher resistivity, like greater than 10 to 100 microamps, the HV for these materials, the HV pulse shape is distorted. Okay, this distortion can lead to a variation in the electric field with time. That distorts that will have a direct distortion effect, distorts the timing resolution. So it will we cannot precisely measure the M/N, mass to charge ratio. So it will directly affect the mass resolution. Okay. So if the material is having a very high resistivity, electrical resistivity. Okay. So even though the material will be having a high conductivity, for brittle material, the yield for the brittle material is much less than the yield for the ductile material, even though these are conductive. Okay. So HV pulsing for brittle material, even though they are conductive, the yield is much smaller than the ductile material. Okay. So this is directly related to the electric field. Why? Because the electric field in APT generates an equivalent pressure which is called electrostatic pressure. Which is up to 10 GPa. Okay. And this electrostatic pressure is almost approaches the theoretical strength of materials. Okay. Other than electrostatic pressure, the HV pulse can also induce the cyclic stress. That these two factors usually increases the probability, increase the propensity for the mechanical fracture. Okay, so mechanical fracture of specimen. So this electrostatic pressure can be given by sigma q square divided by 2 E naught, which is also can be written as E naught F square divided by 2. Okay, so this electrostatic pressure. So here the sigma q is the surface charge density, and F is the field, and E0 is the dielectric permittivity. What is dielectric permittivity? It is nothing but the dielectric permittivity of vacuum. It is nothing but the measure of how easily a material can be polarized by the field. Okay, E0, it is the dielectric permittivity. So for aluminum, the value for P electrostatic is almost 1.6 GPa. Correct. So okay, so this is the pressure which is induces in the material, which can lead to the fracture of the early fracture of the samples. If these are not conductive, then the fracture tendency is much higher because of the distortion caused by the HV pulse shape distortion. Okay, this varies the variation in the electric field, and that distorts the timing resolution, and it also directly affects the mass resolution. Even if it is not conductive, even it is conductive, for brittle material the yield is much lower than the ductile material. Okay, so and this HV pulsing, both cyclic stress and electrostatic pressure is induced on the tip surface, and this electrostatic pressure is given by sigma q square by 2 epsilon naught. Okay, so for insulators or for semiconductors, what we do is, for less conductive applications, what we use is laser pulsing. Okay, so my old atom probes, they were using only the HV pulsing. Okay, so in 1970 Song used a light source in APT. Okay, so light source means this particular light source, it is nothing but it photon assisted field evaporation, field ionization. Okay, or evaporation, field ionization or evaporation. So he has used the light source. So along with Kellogg, they used the first pulsed laser source on an APT. Okay, and since 2006 you can get these laser pulsing, these laser sources. Previously it was sub nanoseconds, now it is available in picoseconds and even femtoseconds. As in the last class I told you, femtoseconds, it is nothing but 10 raised to power minus 15 second. Correct. These have been successfully implemented on the new APTs. So little bit we will discuss about the interaction of this laser with the sample. Correct. So usually on the sample there will be interaction of electromagnetic wave from the laser and tip. Correct. And usually the tip dimension is less than the wavelength of the wave. Okay. So light from the laser pulse will be absorbed on the by the tip or by the tip. Okay, so light from the laser source is absorbed by the tip. So this absorption of light on the tip will increase the temperature. Especially at the surface, at the tip surface. This increase in temperature triggers the field evaporation. Field evaporation. So we need to little bit more understand related to the laser matter interaction. Okay, so in first few femtoseconds, in first few femtoseconds, what will happen is the photon will be absorbed by the electron on the tip. So, or we can tell it as the electron from the tip. The electrons from the tip will absorb the photon from the laser, correct? But even though the electron is absorbing the photon, it gets warmed, it gets heated up, but the lattice is still frozen. The lattice is still frozen. So you will have a combination of electron cloud which is having at higher temperature, plus there will be a lattice frozen system, frozen. Okay, so this is the total system for that. So electron cloud is warmed or heated by the photon. Okay, and this particular system, electron cloud plus lattice frozen, is not in equilibrium. Not in equilibrium. So what will happen? This is not in equilibrium means the heat from the electron cloud has to dissipate towards the lattice which is in frozen. So there will be a electron cloud which is warm. It transfers energy, heat energy to the lattice. This transfer of energy towards the lattice will have some characteristic time. This characteristic time is called electron photon coupling time. Okay, and this particular time is of few hundreds of femtoseconds. Okay, so this is the interaction. This is the briefly about the laser matter interaction. So the electron cloud electrons from the tip surface will absorb the photon. It gets heated up, and but if you see the total system there, the lattice is still frozen. So it is not in the equilibrium condition. So the heat, or there will be a transfer of energy from the electron cloud towards the lattice, and this will have some characteristic time. That particular time we call it as electron photon coupling time, and it is of few hundreds of femtoseconds. Okay, so this time, whatever we discussed about this time, characteristic time, depends on the material and also the shape of the tip. Okay, so therefore the pulse duration, if the pulse duration or the laser pulse, the pulse duration is greater than this characteristic or coupling time, then the electron cloud plus lattice becomes coupled together during the laser pulsing. Okay, remember I am talking about the pulse duration, the laser pulse duration. If it is greater than the coupling time, then your electron plus lattice system becomes coupled during that laser pulse. Okay, this leads to the direct acquisition of energy from laser pulse by the lattice, okay, and due to which there will be a rise in temperature rapidly, rise of the temperature of the tip rapidly, correct. And the peak temperature which can be attained, the peak temperature which can be attained, it depends on the tip material. We'll come to the peak temperature, we'll describe the peak temperature later. So, but the peak temperature on the tip is depends upon the tip material, tip geometry and other various parameters such as pulse duration, wavelength, position of spot and spot focus on the sample, correct. So, these are the parameters which can increase or increase the peak temperature. So, the temperature of peak temperature depends upon these factors, okay. So, in thermal pulsing or laser pulsing, the concept, the main concept is the transient temperature increases due to the absorption of light. It means that the transient temperature increases by the absorption of light from the laser source, okay, and this increase in transient temperature will increase the thermal agitation of the surface atoms, okay. This particular thermal agitation again provokes the field evaporation. Okay, so during when the temperature of the tip surface, increases in subsequent pulses of temperature. So, if for example, if there is a laser pulse, okay, so when first laser pulse is applied, when the tip temperature increases and when during going down of the pulse again it increases too, in between these two time, the temperature of the tip also reduces, okay. So, it means that as the tip surface is heated, this particular heat, as the surface get heat, it will propagate towards the inside the specimen. So, your surface will be treated as quench state, okay. So, there is a successive increase and a decrease in the laser pulse or the specific temperature of the pulse of the temperature. This is leads to this is called thermal pulsing, this is called thermal pulsing, okay. So, the field evaporation takes place at a temperature. So, with this we can see that the field evaporation takes place at a temperature which is higher than the base temperature, okay, and that particular temperature is called the effective evaporation temperature, okay, effective evaporation temperature. Okay, so what is the difference from the HV pulsing? What is the difference? What is the difference of thermal pulsing towards the HV pulsing? So, based on the lambda, the light is absorbed by all materials, correct? Whether it is a conductive material, whether it is an insulator, whether it is a semiconductor, the light can be absorbed by all the materials, okay. So, the first point is the application of thermal pulse, application of thermal pulse can overcome the limitation posed by the HV pulsing, which requires a conductive specimen. Okay, so it overcomes the limitation because of HV pulse, that is, it requires conductive specimen, that can be overcome by the application of thermal pulse. Second thing is the ions, important thing is the ions are accelerated by only the field, electrostatic field near to the tip surface, which is generated by the DC voltage, which is at a constant field, correct. So therefore in this particular thermal pulse or laser pulsing, we don't see energy deficit, we don't see the energy deficit in the time of flight distribution, correct. As in HV pulse we see the energy deficit, that is evaporation of atom, that is polarization of the atom of the tip surface at different location of the HV pulse, okay, not necessary at the high voltage, correct. So this energy deficit is not seen in the thermal pulsing. And the third point which is different from is, here the temperature decreases between the pulses applied of specimen. This temperature decrease is due to the heat dissipation along the tip shank. Okay, so you have atom probe tip, you have a center, so the heat dissipation can takes place either in this direction and also in this direction, correct. So the time to cool down the tip to the base temperature, that controls the uncertainty over the evaporation of ions. Okay, so the time to cool down the tip to the base temperature controls the uncertainty over the evaporation of the ions. Okay, this particular thing will limit the mass resolution. Okay, so this difference in HV pulsing and difference in thermal pulsing, how the mass spectrum looks like, we will cover in the next few classes. But you should understand that the difference between HV and thermal pulsing, HV has a energy deficits, but in laser pulsing this is due to the time taken to cool down the specimen towards the base temperature. This limits the mass resolution. Okay, so as you know that in the tip the light is absorbed. So if you apply a laser, the light is absorbed on the tip surface, so it will absorb to a certain distance, correct. The energy can be absorbed on the tip surface towards a certain distance. This particular distance is called skin depth. So it is the depth through which the light is absorbed into the material. Okay, so we can say that this is the distance of penetration of photon or the light of a wave inside a material. Okay, and this is called skin depth, delta S, correct. And the delta S for a wave which is having a pulsation of omega in a material which is having electrical conductivity E, sigma E, and permeability mu E, can be given as, the skin depth can be given as root of 2 divided by sigma E mu E omega. Okay, so here sigma E is the electrical conductivity of the material and mu is the permeability, fine, and omega is the pulsation of the wave. Further, this particular if this delta s, if this delta is smaller than the mean free path of the electron at given temperature, this equation can be modified by delta S is cube root of 2 lambda E divided by sigma E mu E omega. Here the lambda E is the mean free path. Okay, so there is another model which is called Drude-like model, which estimates that delta S can be estimated by using this mean free path value. You can actually measure, you can estimate the mean free path as me c square ve 2 pi e square ne w. Here the c is the speed of light, okay, and e is the charge, mu e is the velocity, and ne is the density, and me is the mass of electron. Okay, so this is the equation which is proposed by Drude-like model. Okay, based on the if the delta S skin depth is less than the mean free path of electron at a given temperature. So for example, the delta S is equals to, delta is approximately equals 0.2 nanometers for a lambda of 1 micrometer if you calculate for iron, okay. But if you calculate this particular delta S, if which is less than mean free path, delta, we can call it as a delta S analogous. Delta S analogous is given by 30 is calculated as 36 nanometer. This shows that it means that penetration of wave is much greater than the expected. Okay, this is the when your delta is much less than the mean free path lambda E of the electron. Okay, so now we will come to the temperature distribution on the for the volt tip axis. Okay, so Robbins ETL dot, I will give the reference in the PPT. So this particular, so what he has proposed, the whole tip apex is homogeneously illuminated. Okay, and temperature distribution, it means that the temperature distribution along the length of the tip is exhibits cylindrical symmetry. So if you have an atom probe needle, so what he has proposed is the illumination in the tip surface has a cylindrical symmetry. So he has proposed along the tip axis. Okay, it has a cylindrical symmetry. Therefore, the surface can be regarded as heated over at the width of delta S. Okay, and if it is it can be regarded as heated over the heat diffusion from the layer towards the core of the tip over a time t. Okay, so this heat will diffuse from the layer towards the core over a time t. Okay, so the distance over which the heat diffuses is estimated by 2 lambda t t. Here the lambda t is the thermal diffusivity of that particular material. Okay, and this alpha t can be given as K rho Cp. K is the thermal conductivity, Cp is the specific heat of the material, and rho is the density. Okay, so the heat diffusivity D can be given as the distance from the layer towards the core of the tip over a time t can be given as root over 2 lambda t t. Okay, so a pulse of few picoseconds, the distance of diffusivity is around 5 to 10 nanometers for a laser, okay, on the tip material. Okay, so these are the some defined variables such as the skin depth, the distance over which the heat diffusivity will takes place. These are the some terms which variables which are a function of a tip shape. Tip shape. Now coming to another variable which is a peak temperature. So when you are applying a laser, as your tip absorbs the photon from the laser, the tip temperature increases. But what is the peak temperature that the tip surface can get it? Okay, so usually experimentally it is measured that or estimated that this can go up to 800 Kelvin at that particular fraction of pulse. Okay, so 800 Kelvin for tungsten, which is shown, okay, by 5 nanometer second laser pulse. It is estimated. So it is estimate. So this can be estimated for different materials, depending upon the laser pulse, the temperature also can be vary. Okay, based on this there are several works which were carried out to estimate the peak temperature in 1980s. Okay, so in 1980s there are several seminal works which actually carried out to estimate the peak temperature which is attained during the laser pulsing. Okay, so the two key findings from these are, the first is the heat is highly concentrated at the apex of the specimen of the tip. Okay, so this is the first observation which has been proposed by several works, and the second is strong dependence of temperature on the position of spot, the laser spot along the shank and the shank angle. Okay, so these are the two major observations which were proposed during which governs the peak temperature of that particular needle specimen. Okay, so this can be estimated. So how it can be estimated? Remember, in the previous class we talked about the calibration, the relative field calibration versus temperature. Remember, there was a graph which is a F divided by F evap, and there is a temperature, and you can do the calibration. Okay, so we have derived one equation about this, correct? So with by using equation, actually we can, for different kinds of material, we can actually get the calibration curve. Now if this estimation is done by using this particular plot, okay, so it is nothing but, this estimation is nothing can be done as the field necessary to generate field evaporation at a given evaporation rate. So remember, we kept the evaporation rate constant in that equation. Okay, if somebody has forgot the equation, you can go through the previous class notes where you can see that there is an equation which is in between the relative field temperature and the field evaporation. So for a constant field evaporation rate, we can generate the field and the temperature calibration curve, correct? So now in experiment, what we can do is, during the laser experiment, we can measure the total applied voltage okay, is measured, and this value is used by using this calibration curve to estimate the actual specimen temperature. Okay, so with this technique what we can get is that peak temperature can go from 50 Kelvin to 500 Kelvin depending upon the illumination condition. Okay, this is the one method which they use to estimate the peak temperature of the tip surface during the laser pulsing. Another method which is also a reliable method is used as the temperature at which there will be activation of thermally induced temperature at which the activation of thermally induced random walks of atoms. Okay, so this is the temperature at which of for any specific material, for example the tungsten, so the temperature at which there will be a random walks of atoms on the tip surface, that particular temperature indicates the peak temperature which is attained. Okay, so Kellogg has with few nanoseconds and with a wavelength of 337 nanometer, random walk began at temperature, and that increases the random walk begins at a temperature when it is increased to 800 Kelvin with a DC field. Okay, this is the estimation by Kellogg. Okay, and this particular at this temperature this is around 66% of threshold field needed to induce evaporation. Okay, for a tungsten tip. So he has calculated for the tungsten chip. Okay, so these are the two methods where they can estimate the peak temperature of the during the laser pulsing. Fine. So as I told you before that the difference between the HV pulsing and the laser pulsing is that the laser pulsing, the main governing factor is the time to cool down the tip temperature to the base temperature will directly affect the mass resolution. But in HV pulsing, the energy deficit is the factor which affects the mass resolution. Fine. So this is so now the next part is the determination of cooling time. Now we have talked about the peak temperature, and also we can estimate the cooling time. Okay, this cooling time of the tip surface depends on the ability of the tip to transfer the heat acquired. Ability of the tip surface to transfer the heat acquired at the surface towards the core or along the tip axis. Okay, so along the core, towards the core or along the tip axis. So the rate of heat transfer is directly proportional to the temperature differential. What is temperature differential? It is the difference in temperature between the two locations. Okay, so larger is the temperature differential, rate of the heat transfer will be higher. It means that if there are two materials, if there is a tip, if you are putting a laser which is more focused spot on the tip surface, the heat zone is reduced in size. Okay, so it will be locally, it gets heated. So your heat zone will be much lesser if you use more focused spot, due to which the temperature difference between the apex and the shank tip and the shank temperature and the shank of tip will be higher. It means that higher will be the temperature difference. This will cool faster. Okay, so cooling will be faster for this particular. So more focused spot on the tip can be used as a to create a large temperature difference between the apex and the shank of the tip, so that the cooling will be much faster. The another factor is the shank angle. Okay, this parameter also governs the increase. So usually if you have two tips, for example, if you have two tips, one is sharp, very small shank angle, and one is very large shank angle, correct? So this so heat, in this case the heat is diluted very less, but in this case the heat dilution occurs in a large way, is very high heat dilution. Okay, so whichever atom probe tips which are having a shank angle is larger, then the heat dissipation will be much higher, because the heat dilution is much higher. Okay, so it means that the cooling will be much faster. Cooling time. So the cooling time, main parameter to govern the mass resolution in a cooling time. So this cooling time is very important factor to govern the mass resolution in the case of thermal pulsing or the laser pulsing. Fine. So for the, if you want to use a laser pulsing method, usually what we do is the needle specimens are kept thicker, which is having a higher shank angle, not the thin samples. Okay, their heat dissipation will be not much as you see for the thicker sample. Okay, so so the cooling time is more important for the laser for determine the mass resolution. Okay, so as before I told you, in laser there is no energy deficit. Okay, so the mass resolution is governed by the uncertainty of the departure of the ion from the tip surface. Okay, so longer cooling time. If there is a longer cooling time, then what will happen is it will take longer period, okay, and during which the ion gets emitted. So longer cooling time, it means that longer period for ions to get field evaporated. So you will develop a large tail, which we call as a thermal tail. So in the mass spectrum, this is your mass to charge ratio. We will come to this mass spectrum later, and this is your counts. So if you are giving a larger cooling time, or if your tip is very sharp, then what will happen? You will develop a very large thermal tail. So this particular decreases the mass resolution. Okay, so this is called thermal tail in laser pulse. Fine, that limits the mass resolution. Okay, so the next topic is, which I want to just introduce, is the photo assisted ionization. Photo assisted ionization. So if you see, okay, so here I can give an example. So here there is a two tips, which is a very low shank angle, and this is very high shank angle. You can see that the heat dissipation, you can see the temperature profile, the heat dissipation is much higher for this particular case, but the heat dissipation here, it is much lower. Okay, so this particular tip, if you analyze, then you will get a large thermal tail, but here the mass spectrum will be sharper. So this will affect directly the resolution, mass resolution of that part. So now here briefly I will introduce the photo assisted ionization. What is this photo assisted ionization can be understood by three different paths. Okay, so here we have indicated 1, 2 and 3. 1, 2 and 3. So the first one is if an electron from the surface atom can directly tunnel into the vacant bulk electron state. So assuming this is a material, okay, and material has some conduction band, this is a valence band, okay. So if any electron in the valence band gets sufficient energy, it might possible that these electron can go to the conduction band. Fine. So at the tip surface, if you have an atom with an electron, so an electron from the surface atom, it might possible that this field ionization can happen between the three methods. Okay, the first one is, it is a simple like electron from the surface atom. From the surface atom, if it can directly tunnel into the vacant bulk electron state in this direction. This is the one case. Second case, the electron from the adsorbed atoms. The electron from the adsorbed atoms is excited by the resonant absorption of one or more photons. Okay, so if the laser falls on the surface atoms, it might possible that that electron can get excited to the resonant absorption for one more photons. Consequently, they can tunnel into the vacant site inside the conduction band. This is the second method. The third is, it involves the absorption of photons by the electron in the material. Okay, that will create holes in the valence band by the release of electron to the conduction band. Then the electron from the adsorbed atom can go to this particular hole, or can tunnel through this particular hole, fine, into the valence band. Okay, so these are the three phenomena which can describe the photo assisted ionization. Okay, so and the first and third phenomena is enhanced by the large number of electrons in the material. Large number of electrons in the material. At low temperatures, the number of electrons in the conduction band in semiconductor and insulator is negligible. Okay, for this the third process is more dominant. In semiconductors and insulators, the number of electrons in the conduction band is negligible. So the third process, which is that the absorption of energy on the material, which creates a hole by transferring the electron to the conduction band, and the electron from the adsorbed atom can tunnel through and occupy that hole position. Okay, so this is more dominant at low temperature for semiconductors and in insulators. Okay, so this, regardless of this path, these three paths which the electron can tunnel towards the metal surface, the photon induced field evaporation involves creation of an ion on the surface, and it consequently ion on the surface, the adsorbed atoms, and consequently it get accelerated by the surrounding electric field. Okay, so with this, the laser pulse which uses these three phenomena can is actually broadens the application of APT towards semiconductors, functional materials, and also in some cases insulators, where the HV pulsing method is very limited used, which cannot, the yield is very low for the HV pulsing methods. Fine. So these are the three phenomena which can, by which the photo assisted ionization of the adsorbed atoms can takes place. Okay, so with this I will end this class now. So briefly, I'll just we have gone through the pulsing conditions and in little bit detail, difference between the HV pulsing difference and the laser pulsing. HV pulsing, we have discussed that energy deficits are the major concern or which limits the mass resolution. However, in laser pulsing, the cooling time is important to determine the mass resolution. Okay. So, in the next class I will briefly go through a method where we can actually reduce this energy deficit by putting a reflectron inside the atom probe. Okay. With this you can improve the mass resolution significantly. No need to say that laser pulsing definitely it gives higher mass resolution because of the thermal pulse, because of the lack of energy deficits, but and also it broadens the use of APT towards semiconductor insulators and also the some functional materials. Then I'll end this class now and we will meet in the next class. Thank you.